Okay, so let's look at the Kalman filtering algorithm. So this is an algorithm that can be run in real time for tracking. To start out, we set the initial state distribution to something. So I arbitrarily put standard Gaussian here, but it could be any other Gaussian. So as long as it's a Gaussian, it will work. Then prior to observing each new observation at a time point, for example, at time t, prior to observing the value at time t, xt, we form the predictive distribution, which is a Gaussian with a mean and covariance, as discussed on the previous slide. That's our prediction for what we're going to observe next. Then, after observing the value of x at time t, we update the conditional posterior distribution on the underlying state, given the data up until and including time t. And that was also something that we showed how to calculate on a previous slide. So let's look at a very trivial example of this in a plot. So here we have the green line, which is the true trajectory. The blue line is the observed trajectory. And then the red values are the state distribution. So as a function of time, the x's are the means of the Gaussians of where we believe we are at that time point, and the circles are the covariances. So what's some intuition about what this is doing, this tracking algorithm? So we see that in the prior distribution, we add q to the covariance. So when we wanted to calculate this prior distribution on the state at time t, given the data up until and including time t minus 1, we had this distribution. So this is copied from a previous slide. Notice that we always add this q to the covariance. What this is doing is adding some drift to the latent states, adding some variance to the latent state. So at every time point, we're adding some variance and allowing the state to move away, to drift away from what it was at time t minus 1. So this is what's making it a dynamic model, not something that's converging to a point estimate as t increases. We're always adding this covariance to the state distribution, so we're always allowing the model to drift away from the previous state. And then if we look at the posterior distribution of the state given the observation at time t, so this is the prior, not seeing t, xt, and this is the posterior, having seen t. If we then go back and look at those equations, I haven't shown them here, what we'll see is that xt then pulls the distribution away so that st is pulled away by xt so that it can model xt a little bit better. So the prior constrains what st can be, but adds a little bit of drift so it can move a little bit, be permuted by xt, and then xt actually pulls the state in the direction that would have predicted it better. In the next two slides, I want to tie a few of the models we've been discussing together. We can see that in many cases, one model is a modification of a different model. So really, they're very closely related, but by making simple modifications, we get a fundamentally new modeling capability. So first, I want to compare the Gaussian mixture model with a continuous hidden Markov model. So this is a discrete state hidden Markov model with continuous observed values. So we can write the Gaussian mixture model in this way. Remember, we have S different Gaussians, so I'm going to use the same notation that we've used for the Markov model. If we imagine that we have capital S different Gaussians, what we do for the tth observation is we first assign the data point to one of the S Gaussians. So we have a discrete distribution with parameter pi, where pi is our mixing weights, our probability distribution on the S different Gaussians in our mixture model. So we first generate a Gaussian from a discrete distribution with mixing weight vector pi. So we pick a Gaussian indexed by st, and then the observation at time t, given the cluster, given the component it was assigned to at time t, is just a multivariate Gaussian with mean equal to mu st and covariance sigma st. So we pick out the mean and covariance indexed by the state or the cluster at the tth observation. So we have this type of a graphical model where we pick a state from a probability distribution. So I could also say that we have a vector pi here, and then we simply pick a state based on this vector pi, this distribution pi, and then given the state or given the cluster, we generate the observation from the Gaussian picked out by that cluster. With the continuous state, with the continuous discrete state hidden Markov model, what we now have is that the state at a particular time is generated from a discrete distribution where we pick out the probability distribution indexed by the previous time point. So A is a transition matrix. It says that if we're at state st-1 at time t-1, then we transition to the state at time t according to the distribution indexed by the row of our transition matrix st-1. And then given that state, we again generate our observation from a Gaussian where we use the mean and covariance picked out by the indexed state. So notice that given st in both of these models, we simply generate the data from a multivariate Gaussian with the mean and covariance picked out by the index s. However, for the Gaussian mixture model, we're picking the clusters, or picking the states, if you will, from a discrete distribution that's always using the same probability vector pi. Whereas for the continuous hidden Markov model, which is a discrete state model, we're using also a discrete distribution, but we're picking out the distribution according to a transition matrix. So we have, if there are capital S different states, we have capital S different probability distributions that we could possibly choose, and we choose the one indexed by the previous state in order to generate the next state. So they're very similar in that way. So there's a similar comparison that we can make between probabilistic PCA and the linear Gaussian Markov model. The previous example was this comparison between two discrete state models, if you will, the Gaussian mixture model that had no sequential distribution, and the continuous hidden Markov model, which did have a sequential distribution on the discrete states. Here, if we look at probabilistic PCA, we see that there's a similar model structure as the Gaussian mixture model. So I'm using the notation that we used in this lecture to discuss the algorithm we discussed in a previous lecture, probabilistic PCA. So here we have a vector st for the tth observation, which is generated from a multivariate Gaussian with mean 0 and covariance q. And then given the vector st, we generate the observation at time t, or the tth observation, from a multivariate Gaussian with mean equal to a matrix D times the latent vector st and covariance v. So in the previous lecture, when we discussed probabilistic PCA, we used different notation. I believe this was W and this was C, something like that. Here I'm using the notation of today's lecture. So you see that the latent state, if you will, the continuous state vector, is a continuous random variable, but there is no sequential information being modeled. So we have, again, something that looks like this, where each state is generated IID from the same distribution, so there's no sequential information, but now it's a continuous valued vector instead of a discrete index. If we now take probabilistic PCA and we build a sequential model on top of it, we see that we have the linear Gaussian Markov model discussed today, where the state at time t, given the state at time t-1, is a multivariate Gaussian, where we have the same covariance, but now the mean is equal to c times the state at time t-1. So we again see that the latent state at the previous time point informs the latent state at the next time point according to this function. But then given the latent state, we have exactly the same distribution on the observation as with probabilistic PCA. So again, with discrete state models, Gaussian mixture model and the continuous hidden Markov model are essentially the same in the data generating distribution, but fundamentally different in the way that the distributions are picked. One has an IID distribution on the latent Gaussians, and one has a sequential distribution on how these latent Gaussians are picked. With a continuous state model, we have probabilistic PCA, where again the distributions are identical on the observations, but on the latent states, for probabilistic PCA, they're IID from a continuous Gaussian distribution, in which case these aren't even referred to as states. Whereas with the linear Gaussian Markov model, we have a Markov sequence generating these latent states. Finally, I want to discuss a few of the many extensions of this modeling framework. Each of these would require a modification to the algorithm we discussed previously. They're not trivial modifications, but they would look familiar based on what we've discussed. First, there's the nonlinear Kalman filtering framework. So what a nonlinear Kalman filter does is it takes exactly the same state sequence as before, but then it generates the observation by using a nonlinear function of the state sequence. So previously we had a matrix times the latent state, so it was a linear function of the state, in which case everything was nice in closed form using Gaussians. Now we have a nonlinear function of the latent state, in which case calculating the posterior of the latent state is no longer in closed form. So this happens quite a bit with systems where we don't get linear measurements. For example, we might get functions of locations based on angles and whatnot, and distances. So with the nonlinear Kalman filter, there are many ways to approach this problem. One way is to use what's called the extended Kalman filter. What this does is makes a simple approximation to this nonlinear function. It treats this nonlinear function of st as approximately equal to the function evaluated at some point z plus this gradient matrix times the difference between the latent state and the point z that we pick. So it replaces this nonlinear function with an approximating linear function. If we take this function and place it in the mean, again we have linear functions, and so everything's Gaussian. We might also want to modify the models so that we can take continuous time into account. By continuous time, what we mean is that the time difference between two time points is not always the same. For example, time t and t plus 1, we might have had a few seconds elapse, whereas between time t plus 1 and t plus 2, we might have had a few milliseconds elapse. In that case, we modify the model in this way. We have exactly the same observation level distribution, but the state distribution on how the states are evolving now has a function delta t times q on the covariance, where delta t is the time lapse from the previous time point. So we have q, which is a constant matrix, now being scaled up or down based on how much time has passed. And so this is a Brownian motion representation. We can also add control to the system. So in this case, we have our state evolving distribution like this, where we say the distribution on the next state given the current state is a Gaussian, with this mean equal to a sum of a matrix C times the state st, as before, plus a new thing, g times ut, where ut is a vector that we get to control. We say what u is. For example, it could be a thruster along a certain dimension, power that we're going to put into the system. And so this is how we can control the latent state in order to control what we observe in the observation sequence xt.